So thank you very much for the kind introduction and for inviting me and for organizing this great workshop. So this talk is based on joint works with Christian Nickenmeyer, Gorav Jindal, Vladimir Lishikov, Anurag Pandey and Frank Olaf Schreier. And I will mainly talk on one work of some subset of these authors, but I will also briefly mention some recent result with another subset of these authors. And so this talk will be about algebraic proof. So essentially we are interested, how hard is it to prove that some point lies in some specific variety? And that also tells you something about GCT, because by the end of the day, if you have a multiplicity obstruction, you have proven that some point is not contained in some orbit closure, so there has to be some equation that vanishes on this orbit closure, but the point does not vanish on this equation, right? You don't have to write this down explicitly, but it exists. Yeah? And so I want to talk a little bit about these connections, but it will be like the talk before, more down to earth, so we will really be able to prove something, but only rather tiny things. So that's okay. So and it starts with some algebraic variant of this natural proofs, and so maybe you all know natural proofs, but I just will briefly tell you something about it. So this is an excuse why we are so bad at proving lower bounds. And so in the Boolean setting, this was done by Ratzboff, and Rudik, and so we have some property P of Boolean functions. We call it natural if it satisfies these three properties here. And I should mention that compared to the original paper, I flipped. I replaced P by the complement of P. Yeah? And this is because in the Boolean setting it doesn't matter, right? Because if you want to flip 0 and 1, you just do the negation operation. But I want to talk in the algebraic setting, and they have 0 and non-zero, and there's no algebraic operation which switches between these two things, and so it's better to look at it in this way. Yeah? And I already also set the parameters to the most used setting here. So we have this usefulness. So whenever I have a function that's easy to compute, which means poly-size circuits, then it should have this property. And it should be constructive. So if I give you the truth table of some function, you can decide in poly time in the size of the truth table whether it has this property or not. And it should be large. We want to have this largest condition. So random functions don't have this property with some probability. And then, first of all, most or almost all of the known lower bound techniques they are natural. They have natural properties. And then Ratzboff and Rudik go on and essentially they show this barrier result. So whenever we have a natural property P, it can distinguish between a pseudorandom function having poly n-size circuits and a truly random function inside exponential time. Yeah? And the conclusion is, if you believe in some variant of public key cryptography, then no natural proof can show super polynomial circuit lower bounds. And essentially, the question is, so now we have an explanation why we are bad at proving Boolean lower bounds, so we need also an explanation why we are bad at proving algebraic lower bounds. And so one of the problems, of course, we don't have any concept like a one-way function in this algebraic setting. And so therefore, last year, so there were essentially two independent papers, one by Forbes, Spilker, and Volk, and the other one by Groscher, Kumar, Sachs, and Saraf. And they introduced these algebraic natural proofs. Yeah? Essentially, I always want to have this setup here. So I have some set M of monomials, and I look at the linear span of these monomials. That will be my ambient space. So you could think of M being all the degree D monomials. So we look at all these monomials, or all the monomials for every variable is the degree bounded by D. So this is, and then I always have some class C inside the span of these monomials. So you should think of C being, say, some easy polynomials. So for instance, have polynomials having poly-size circuits. And then I will have some class D. And in D, for every monomial in my set M, I will have one variable. And essentially, you could think of, I want to take the coefficient vectors of my polynomials in C, and I want to plug them into D. So essentially, D will tell me something, so whether D is 0 or not, will tell me something about whether C is hard or not. Yeah?
What is Tm?
Tm, so this is a variable. So for every monomial, there's a variable which I simply call T, and I will index simply it with the monomial. But you could also say it's T1, T2, T3, T4, and so on, and I just number the monomials for 1, 2, 3, 4, and so on. Okay. It's just a notation. So what I want to do, the coefficient of the monomial m in a polynomial from C, I want to substitute this for the variable Tm. So that's why I have this notation. And then some polynomial D in my class D is an algebraic D natural proof against this class C if D is the non-zero polynomial, and for all f in my set C, D of f vanishes. And this means if I take the coefficients of f and plug them in for these variables here, then the polynomial is 0. So it's essentially, and now if you say you have to have, say, if you think of C, say, as Vp, and you have an algebraic natural proof for Vp, then you can take a polynomial, you take the coefficient list, you plug it into D, and if it doesn't vanish, you know that your polynomial is not in Vp, so you have proven lower bound.
One could also say it's a non-zero element with a vanishing ideal. Or is there anything different from that?
One could also say it's a non-zero.
No. What, I mean, the C, I mean, it has a vanishing ideal.
The C has a vanishing ideal, and of course, yes, you have a non-zero element and a vanishing ideal. This is what you also could say, yes.
That is what you're saying.
Yes, it's the same. It's just a more, it's a more concrete.
Okay.
Yeah.
Because I got really confused.
So this is the original definition, essentially taken from the paper from Forbes, Spilker, and Volk. So that's.
So,
Make the connection.
Yeah.
a natural property usually has a third property, largeness, but this is kind of like inherent just because you can't have two.
Essentially, in the algebraic setting, you get largeness for free, because you have a polynomial and the non-zero elements is always an open set, so almost all the elements don't satisfy your property. Exactly. And of course, now you want to have some barrier, and so the way this barrier was formulated by those two sets of authors, which are was with succinct hitting sets. So, and you all know what a hitting set is. And so a succinct hitting set is now the following. So I have my polynomial, my class C, and I have my class D again. And then H is a C succinct hitting set if H is contained in C, and H viewed as a set of vectors of coefficients of length m is a hitting set for my class D, so for the class of my proofs. Okay. This means that hitting sets for D, they can be written as the coefficient vectors of polynomials which come from some easy class C. So that's the intuition. And then from the definition, it's almost...
Wait.
Yeah.
No. Okay.
Yeah, and from the definition, you already get essentially this this barrier, so the succinct hitting set barrier. So there are no DL natural proofs against the class C, if and only if there are no succinct hitting sets for D. Yeah? So you now say you can set the parameters. So for instance, if you have n, capital N and D, so you look at all the degree D monomials, then essentially there's no algebraic poly and D natural proofs against this class C if there are no poly and D succinct hitting sets for such size circuits in ND variables. And you can even specialize this even more. So if you just...
So what do you say for VP?
So for VP, it will essentially say this. So for VP, you would also have D is poly n, and then poly n is polylog in the number of the big variables. Yeah? And for VP, so you could, this is a conjecture, a wish or a fear now, that there are no poly log n succinct hitting sets for poly n size circuits. But we don't know that. So this is the so if you assume this, then you can't prove there are no natural proofs which would prove lower bounds against VP.
So Markus, in the previous slide, you had an if and only if, whereas in the Boolean setting it was an only, it was maybe one of the two, right? It was not bidirectional.
Yes, but here it's an if and only if,
Here
because
it's an if and only if. Okay.
just by definition.
Okay. All right.
But of course, it's not clear. So at least it's not clear whether these succinct hitting sets should exist or not. So then Forbes, Spilker, and Volk, they for models for simple models where we also know lower bounds, they prove essentially that these succinct hitting sets exist. So therefore, we can't have these. Therefore we can't have these natural proofs. And so our motivation was now, since we don't know how plausible this conjecture is, can we replace this by something different? So can we replace this by something more plausible? And essentially we did this by somewhat changing the game a little bit. So this original motivation came from tensor rank. So you have, you all know this, so tensor T has rank 1 if you can write it as the tensor product of 3 vectors, and then the tensor rank is the smallest number such that you can write the tensor T as a sum of R rank 1 tensors, and SR, so capital SR, will denote the capital SR here. This will denote the set of all tensors of rank at most R. Yeah? And then you can essentially play the same game. So you can now ask, what are lower bounds? Can you prove lower bounds for tensor rank with these equations? Yeah? And so you could say, and now that the game somewhat changes because, or you could also think of T being a trilinear form, so you again have polynomials, but now you don't have a jump in the number of variables. So in the previous, we had n variables, and the proofs had exponentially many variables. Yeah? And here, essentially, the proofs only have polynomially many variables. So that's the difference in the game. Yeah? Then you could say, so NAD is a poly KMN natural proof against the set SR if D is non-zero. D vanishes on the set of all rank R tensor, and D is computed, say, by poly-size circles. So this is some natural proof against this class. And the good news, so the good news for me, because I want to prove some negative result, is that tensor rank is NP-hard, which was shown by Johan Hofstad a long time ago. And even better, so it's even much harder. So Shitov and independently Schäfer and Stefankovic, they proved that it's even as hard as the existential theory over the corresponding field. So if the field is finite, it's NP complete. But if the field are the rational numbers, then it's as hard as the existential theory over the rational numbers.
This is for three-dimensional tensors?
This is for three-dimensional tensors, yeah. The bad news, of course, is that SR is not a zero set of polynomials. And when D vanishes on SR, then it also vanishes on its closure. And then XR, it can only describe the set of tensors of border rank at bounded by R. And therefore, in particular, this XR has to contain some tensors of rank R, because otherwise tensor rank and border rank would coincide. And the bad news now is we don't know whether border rank is NP-hard. And we tried for some while to prove this, but we failed. And therefore, when you can prove anything, you just modify the game. So we looked at some different quantity, which is motivated by some machine learning and network coding applications, which we would call the completion rank, or the generalized matrix completion problem. So essentially, here we have given M matrices. You can think of this being the slices of a tensor. This is again a problem on tensors. And so the completion rank of such an instance of matrices is the minimum number of R, such that you can find scalars lambda 1 to lambda m. And you look at this linear combination here. So you always have to take the matrix A0. Then you can add an arbitrary linear combination of the other matrices. And you want to bring the rank below R. Yeah? Whenever you can do this, the minimum R for which you can do this is the completion rank of this tensor. You can also think of phrasing this in terms of an affine linear matrix. So you have a matrix, and the entries are affine linear forms. And then you're asking, how can I instantiate my variables such that the rank drops below R? Yeah? And it will switch freely between these two settings. Okay, and this has some motivation from machine learning. It's also called the Netflix problem. So we are really working on something relevant here for the Netflix problem. Yeah, I don't know. So essentially, this Netflix problem, you usually have a matrix, and
He's from Germany.
I'm from Germany. Why?
Because you said this is something relevant.
Netflix? No. So I don't have a Netflix problem because I don't have Netflix. I had some of my kids say, we have a Netflix problem because we don't have Netflix. So that's so that's a different view. So why it's called the Netflix problem, essentially, you can think of having a partially filled matrix, and you want to fill the entries such that individually from each other, such that the rank of the matrix becomes very low. And the entries that you know is that user A, which are the rows, and you have the columns, which are the films. So user A likes user B, and then Netflix says we are making billions of dollars with bad content. So users have to be really simple-minded, and this is reflected in the case that the rank is low of this matrix. So that's so this is why this is called the Netflix problem.
So the AIs are supposed to be basically singletons, one.
Yes, and so in the Netflix problem, these are just the singletons, and they're just these are just the matrices here, which has just 1, 1 in some position, and they're 0 everywhere. Yeah, but just very natural to look at this generalized problem. Okay, and
it's essentially matrix rigidity, right? In this sense.
Here you're given specified entries that you can change arbitrarily.
Yeah, but you can't. So these fix the positions where you can change, right? In matrix rigidity, you have to find the positions where you change, such that the rank drops. But here, the positions where you can change are given to you, and they might be even connected to each other. Huh? So it's related, but not the same. And how can we now phrase this? So you can now look at the following things. So you take all these matrices, you take all the scalars, and so if you look at all these things here, such that the rank of the sum here is bounded by R, then this is a closed set because you can describe this by the vanishing of the R plus 1 times R plus 1 minus. So this is a variety. And we denote this by PM and R. And of course, to get the object that we're interested in, these would be all the tensors of completion rank R. So you project away these scalars lambda 1 to lambda n. And this gives you the set of all tensors here that have completion rank bounded by R. But unfortunately, this set is not closed. So there's an easy example. So for instance, let's do this one. So this is your one matrix. A0, you have to take this matrix, and you can add this matrix freely to this one, but no matter what multiple of this matrix you add to this one, you always have a rank 2 matrix. Yeah? But if you now work with approximations, so you can approximate this matrix here by that matrix. Just think of epsilon being small. And then you add 1 over epsilon of this matrix here, and you get that matrix, and this is a rank 1 matrix. Because if you multiply the first row by epsilon, you get a second row. So you can approximate this instance here, which has completion rank 2, by instances which have completion rank 1. Yeah? And this is in the Euclidean closure, but by general principle, this is also in the Zariski closure. And so therefore, so we need to look at the closure here too. But there's one caveat how to take the closure. There's some subtle thing. You have to be careful if you take the closure with respect to the wrong ambient space, you will get some meaningless results. So here's a very easy example. So take B be any rank 1 matrix, and now this is the identity matrix of size n by n, say. And you look at this example here. You have to take this matrix, and no matter what multiple of B you subtract, you can drop the rank by at most 1. And this is basically in the algebra. But if you now work with approximations, you can approximate this low rank matrix B by this high rank matrix. Yeah? So this is high rank. And if you now subtract this here from that, you get a matrix which has rank 1. Yeah? So you can, by approximating low rank matrices by high rank matrices, you can drop, there's a drop from completion rank to border completion rank, which can be arbitrarily high, and that's maybe not nice. And so therefore, we take the closure with respect to this space here. So we want to approximate these matrices B here only by matrices that have rank not larger than the rank of the matrix itself. It's not so nice, but it seems to be necessary. So we take the closure here in this space here, or in this variety here, where this is just means, so this is the set of all m by n matrices whose rank is bounded by row. And R1 to Rm are now the ranks of our matrices A1 to Am in our instances. Okay. This is some, but I will also later talk on, there are some ways to get rid of that. And now we can define a border completion rank. And so this is all the instances here. And now we approximate where we can approximate our matrices AI here by matrices AI tilde. And the rank of AI tilde is bounded by the rank of AI. And we can find rational functions in epsilon such that the rank of this thing here is bounded by R. So this is now the border completion rank. So we approximate, so we have polynomial approximations to the matrices and rational approximations, rational functions here in these constants. And the whole thing should be bounded by R. And this is what we call the border completion rank. And it's essentially, you can also take the Euclidean closure in the ambient variety that we have defined, and by general principles, this will give exactly the same quantity. And essentially what we now can show is that deciding border completion rank, that's an NP-hard problem. So we couldn't show this for tensor rank, but deciding so border completion rank is NP-hard. Yeah, so we understand the border essentially that well that we can prove NP hardness for this. Yeah, and,
can this also be characterized topologically, this border completion rank, and without the epsilon?
I can also write this as an orbit closure. What do you mean by?
Yeah, okay.
Yeah.
This, you can do that. What is the group there?
The group is not so nice. In particular, I don't know whether it's reductive because this is an affine problem, so you can't change this first matrix. So you have general left-right actions, but when you want to, so you have, if you think of a tensor, from two sides you can multiply with GLN matrices, but from the third direction you can only multiply with GLN matrices which keep the first slice fixed. Yeah. Because you're not allowed to multiply by 0.
It's like an affine group.
It's like an affine group, yes. Yeah. So I don't know whether this is, for instance, reductive. I don't have a counterexample, but it's not clear. But I also don't have proof that it is. Okay, and so how can you prove this hardness? So you can hardness of completion rank. It's easy to prove, and it was also known. And so here we reduce from 2CNF set. So of course. 2CNF satisfiabilities is of course in P, as you all know. But if I give you a bound and ask whether you can satisfy at least B of your clauses, that's still an NP-hard problem. And we reduce from this. And the instances will be very, very simple. So essentially all the matrices, they will just be they will just have 2 by 2 blocks on the diagonal. So this will be a super simple instance, which allows us to control this limit process and still get the NP hardness. But let's first look at the completion rank, because the construction for border completion rank will be similar. So when you have a clause Ci, which is a literal L1 and a literal L2, then our gadget will simply look like this. So think of this being on the diagonal. So on the diagonal we have 1 minus L1 and 1 minus L2, and L1 is say xk if the literal is positive. So this is 1 minus xk standing here. If the literal here is a positive literal, and it's just 1 minus xk, so there's just an xk standing here if the literal is negative. Yeah? And that is very easy to see. This matrix has rank 2, unless you set one of the variables such that the literal becomes 1. Yeah? Because then you will either have a 0 row or a 0 column, and the rank drops. That's already essentially a hardness proof. Yeah, so now you put everything on the diagonals, and then it's very easy to see by what I said. So if the border completion rank is bounded by 2s minus b, where s is the number of variables, s is the number of clauses, then this is if and only if the b clauses of phi can be satisfied. And we don't need any variable gadgets here because you can't drop the rank if you set something nonsense like 2 or pi squared over 6 or something like this to your variables, you won't drop the rank. Yeah? So that's essentially a lost variable whenever you do this. And the nice thing now about these instances is that they are super simple. So you have, so if you just go back, can I go back? If you just look at this matrix here, so essentially there's just one variable standing here, there's one variable standing there. So in every row and every column there's only one variable standing. And all the ones here, they go to your matrix A0. Yeah, so all the A1 to AM, so the matrices that you are free to choose, they are just diagonal matrices with the property that in only one end matrix has a non-zero entry in one diagonal place. So whenever you look at a place on the diagonal, there will only be one matrix which has a non-zero entry there. And this makes everything super nice because we can now go on, and essentially if you now have approximation to these matrices here, then you can essentially find invertible matrix S and T, and they don't change the completion rank, such that this transformed instance here is exact in the matrices A1 to AT, and they only approximate in this matrix A0. So that's the crucial property. And essentially you can just do this by, if you take these approximations here, you just do row and column operations to clear everything off the diagonal. And then once you have cleared this, then by this rank restriction, you know that this matrix is exact. And because the diagonal places, there's only one element on every diagonal from one matrix, this clearing doesn't interfere with each other. Right? This essentially, so you have the approximations you can make it almost exact. The only approximation you have in the end is in this A0. And then essentially the same proof works. The same proof works for completion rank, and now also works for border completion rank. So if you look, the one direction almost direct for some completion rank, and otherwise now if you have some lambda I, and these can now be rational functions in epsilon, so that this di can in particular be negative, such that this rank is bounded by 2s minus b, then the claim is that this also induces an assignment on the xi into the literals Lj, such that I can satisfy b clauses. And if you now look at this, we say essentially to have rank 1, if this locally should have rank 1, then this L1 should remove this 1 here, and it should not introduce any negative powers by epsilon. Because here, only on the diagonal, there can be negative powers of epsilon that they can't cancel out. So once you have introduced negative powers of epsilon, essentially you have wasted your variables, and you could improve on the completion rank by taking some useful values to this. This is the main idea. And once you have done it, we call a clause epsilon satisfied if L1 and L2 is of this form. And if you have these epsilon satisfied clauses, you can set epsilon to 0, and you get an partial assignment to some variables which satisfy B clauses, and to all the other variables you don't know, but you don't care. You can set anything there. You make it some 0-1 assignment, and in this way you can see that also the border completion rank problem is NP-hard. The main property is essentially that these instances here, they are so simple that you can control the error. That's the main property. And now you can look at algebraic proof for the border completion rank. So we have a tensor T and an algebraic Pauli and natural proof for the border completion rank. For some tensor T, for the completion rank of some tensor T being greater than R, is a polynomial P such that P vanishes on all tensors of border completion rank at most R. P is computed by a polysize circuit. For simplicity, it should be constant free because I don't want to. I want to guess the circuit later on, and I don't want to remove the constants now. And an additional problem, so it should be a proof for T, so I want that P of T is non-zero. That's the new thing that I want. Okay. And so what I need is, so the idea is I want to guess the proof, and I want to check that it vanishes on this variety here. But I don't know this variety, but I know a dense set in this variety, and this dense set is the set of all tensors of completion rank bounded by R. And I want to efficiently generate this set of tensors bounded by completion rank R. And essentially I want to do this by some polynomial. I want to have a tensor, the entries are polynomial, and then when I look at this tensor, when I substitute arbitrary values for the values in the polynomials, I want to get all the tensors of completion rank bounded by R. Yeah? And how do I do that? Well, it's very easy to generate, say, all the matrices that have rank bounded by R, because we just take, so this thing here is a generic rank 1 matrix. If I sum up row of them, and I now substitute values for all these variables, I get all the rank row or rank at most row matrices. I could also get rank matrices of rank lower than that. Yeah? And now to generate all the tensors that have border completion rank bounded by R0, yeah, I just take here these constructions that I have here. So now I have matrices Q1 to Qt, which have some rank, if I R1 to RT, which are given by my original instance. And now, to have border completion rank R0, I want to have some matrix R0 here, and when I should be able to subtract these matrices here from whatever I have here to reach something which is R0. Yeah? And in this way, I get a tensor which has polynomials as entries, and the map, the image of this map will be all tensors of completion rank, of completion rank R, R0. Yeah? And what's this good for? So I can.
How large do you need T to be here?
T will be given by my instance. So I will have, I'm looking at n by T tensors, and it will simply be given by the instance. Yeah, so this is just a parameter. Yeah. So this is essentially now the main result. So for infinitely many n, there's an m and some tensor of the size n and m, and some value r such there's no poly n natural proof for the fact that this border completion rank of this tensor is bounded by R, unless co-NP is a subset of X, there is BPP. In particular, the polynomial term hierarchy collapses. And how do you do this? Essentially, we want to prove, so we have a formula phi in 2CNF, and we want to prove, and some B, and we want to prove that every assignment satisfies at most B clauses of phi. And this is a co-NP hard problem, and we want to do this in there is BPP. And how do we do this? So assume for the contrary that for almost all n, and for all m, and for all tensors t, and for all values r, there's a poly n natural proof. Yeah? And then we take, out of this phi, we construct the tensor in the hardness proof. And then we get a circuit C of polynomial size computing some proof P. And then we need to check that P vanishes on the set of all tensors of border completion rank. Yeah? But this we can do by using polynomial identity testing, because we have this universal tensor G here, which is a tensor with polynomials as entries, but the image generates all tensors of completion rank R. Yeah? In particular, if this polynomial P vanishes on all the tensors of completion rank R, it will also vanish on all tensors of border completion rank of R. Yeah?
What is R here? Because like it's trivial if R is equal to n times m times n squared times m.
R is of course also the value that you get out of the hardness proof.
But like, how large is it? Is it like n? Is it like because if it's greater than n squared m?
No. So R is the completion rank of some tensor here can be at most n, because it's the rank of the matrix that you can build. Yeah. And then this B is now whatever for whatever regime 2CNF testing is the NP hard. So I forgot the exact number. It's some constant, but you can really compute it, right? So it's nothing which you don't really know it in advance.
So it's constant times n.
It's a constant times n for some constant smaller than n. Yeah. Okay. Yeah. And so you just take this tensor and you just check by polynomial identity testing that it's 0. Yeah? And this is there is for guessing the circuit. This is BPP for the identity testing. And then you just have this another identity testing instance. You just have to test whether P of on this tensor does not vanish. Yeah? And if yes, we accept this phi, and otherwise we reject. Yeah? And so this is now there is BPP protocol for co-NP complete problem, and therefore we have this inclusion. Yeah? So, for instance, if you believe that the polynomial time hierarchy collapses, then for this problem, you can't have, for every tensor T and so on, you can't have algebraic natural proofs or proof of polynomial size.
I try to understand in another language. Now, does it say every non-zero polynomial in the vanishing ideal of those? Oh no, the tensor is fixed. It's not a.
No, I can only for specific tensor. So there's a sequence of tensors such that no, for this specific tensor, you can't have a poly-size proof. But of course, the equation, the variety could have easy equations. I can't rule that out. Now I'm a little bit out of time. We can also write this as an orbit closure problem. So you could write this as an orbit closure. It's not too hard. The problem is, so the group might not be reductive. And the closure is taken in some variety, not in some vector space. So that's maybe not so nice. But the good news is in some very recent paper, not online yet somewhere, we can also look at the homogeneous variant of this problem. So we are now also allowed to take a multiple of the first matrix. But of course, now you have to rule out it should be a non-trivial linear combination. You don't want to take all 0, then the rank is 0, but that's not interesting. So it should be, so it's projective now. You look this in the projective space, and this is also NP-hard. Also checking whether this, we call it now the min rank, or this border min rank problem, this is also NP-hard. And the closure is taken with respect to a vector space now. It can be written as an orbit closure. The group is now the normal group that you let act on tensors. In particular, it's reductive. And the other nice properties of the generating tensors of these orbit closures, they're also described by the symmetries. This is exactly the ideal setting that you want to have in the GCT set. And in particular, what follows from this is also that for these tensors, so the orbit closure containment problem is NP-hard. Unfortunately, we don't state it in our preprint like this. It follows directly, but we don't state it explicitly. So if by chance someone is reading it currently, so keep it in mind, right?
So I think it's very remarkable in view of Ketan's talk, who says, predicts or conjectures that the orbit closure intersection problem.
Yeah, so we of course we tried also to make it work for the orbit closure intersection, but we don't know. It doesn't work for the techniques that we have. So the containment is hard. Intersections we don't know. The intersection is not that easy. For a while I thought it would be easy, but there are some very subtle things that can happen, and it's not so easy to prove. Okay. Seems that I run a little bit out of time, so let's speed up a little bit.
We have about 7 minutes.
7 minutes, yeah. And maybe I'm through half of my slides, so it should it should work. So, relation to tensor border rank. So this is essentially the theorem that's used and it's very easy to prove. Is so how this completion rank and rank are related. So if these things here are rank 1 matrices, then essentially we have this relation between rank and completion rank. So the rank of this corresponding tensor is the completion rank of this tensor plus m. And this is essentially used in this hardness proof by Šéf and Stefanković, for instance. They simply used this one. And we wanted to use this for border rank. Unfortunately, so we failed. So one reason why we failed is that we only get this side of the equation, not the other one. And the other reason why we failed is these matrices have to be rank 1. And then all of a sudden you get some solutions in the border which you don't want to have, and that messed up everything. But what we could do with this is we could prove that with similar techniques that the tensor rank is NP-hard to approximate within 1 plus epsilon for some constant epsilon. And so it's independently, that was also proven by Song, Woodruff, and so most likely these two names are pronounced differently, but I don't know how. So it's Song, Woodruff, and Song. And also Joseph Swanovsky, maybe I saw him yesterday. Ah, you were sitting there. Okay, great. Yeah. And so it's very funny. So I remember it was early 2000. I went back on the train with Johann Hastad from Oberwolfach, and then he told me, oh, it would be great to know that tensor rank is NP hard to approximate, but it's so complicated, and these approximations can do so much things with the tensor. And now it took, I don't know, something like 15 years, and now all of a sudden we have three different proofs at the same time. Yeah? So that's
means it's time for proof. It's the right time for proof.
It was the right time for the proof, but so apparently we didn't know of each other. So there was nothing which somehow stimulated this proof. It just
Are
was
we different proofs or the same?
So here, this proof. So they essentially prove a stronger hardness result, but under ETH. And this is a paper which has more than 100 pages, and this is somewhat in Appendix H or something like this. So I didn't check it too. I just had a quick look at it. Here the proof is so we use a different construction. Yeah? So it's I don't know what's similar. And so
It's somewhat similar.
It's somewhat similar, but it's also somewhat.
It's totally different.
Yeah. So I know. Okay, just so the gadgets now, before I had these 2x2 gadgets, now the gadgets look like this, right? So it's just a little bit more complicated. Let's just skip this. What I want to, just in the remaining 3 minutes, I want to look also at some toy example like Christian did, but which is very meaningful. So I want to look at this variety Zn, and Zn is the variety of all matrices. Is it somewhere? I don't know. The Zn is the variety of all matrices with, it's standing here, with permanent 0. Okay? You look at this variety. And then very similar to what we did before, you can prove that Zn has no, if Zn would have an VP0 natural proof, then P to the sharp E would even be contained in there is BPP. But it's somehow you would expect this somehow, right? Because Zn is a hypersurface. It's described by the equation permanent equals 0. Permanent is irreducible. So the only equation which can describe this variety are just powers of the permanent, multiplied by something. And then with a very similar construction like before, if you would have these proofs, you could guess them. You could verify that they vanish on this permanent set. You use the self-reducibility of the permanent to do this. And then you could get a circuit for the permanent by using Kaltofen factorization. And then you could get, if you have the circuit for the permanent, you can prove that P to the sharp is contained in there is BPP. So a very similar proof. If the polynomial term hierarchy collapses, then there are no VP0 natural proofs against the permanent variety. On the other hand,
so K is what kind of a field?
What?
K, what kind of a field?
K, you could either it's a large enough finite field, but then you don't get the asymptotics, or you just take say the rationals. But we want to be able to compute modulo P for this construction to work.
Markus?
Yeah.
In the fourth step, how do you generate a matrix, a random matrix with permanent 0?
No, I don't generate a random matrix. So what I do is essentially, I look like before. I have some polynomial. And this polynomial matrix here, this describes all, if I substitute the values, I get all the permanents, all the matrices that have permanent 0. But to describe it, I need a circuit for a smaller permanent. So I use the self-reducibility and you do this step several times to get this thing. Yeah? So I don't substitute.
It's a bit different from the universal map that you had in the earlier.
It's somewhat different, but only because I use self-reducibility. But the idea is exactly the same, just the construction is a little bit more complicated. Because I have to use it several times to get this.
And Markus?
Yeah.
The VP0 just refers to constant free.
Yes, it's constant free 0. Constant free circuits. Because I want to guess. You want to guess them, and you want to deal with constant that you need to remove. So just one thing that I want to say is that also we don't have a natural proof. You can get an occurrence obstruction in a GCT framework for this variety. So I'm now really running out of time. So what is the group action that we have? So we have the action are the monomial matrices. that will act on, and this keep the permanent fixed, or the zeroness of the permanent is fixed by action with these monomial matrices. And now the only point is, so now, what you essentially can do is, if you look at this thing here, so the permanent is of course in a coordinate ring, yeah? Because the permanent vanishes on this variety just by definition. Yeah? And if you just look at this thing here, so these are just n, it's just n ones, and this is just length 1. If you look at this, then this essentially describes the permanent. Yeah, so there's a compact description in this GCT framework of the permanent. Yeah? So this subrepresentation here is the permanent, and it has multiplicity 1. Yeah? And if you look at an orbital closure of the matrix A, then the multiplicity of this thing here is 0 if A has permanent 0, and otherwise it's 1. Yeah? And in this way, and I'm now, yeah, I know the drinks are waiting outside. And this way you get, in this toy, this is again a toy example, but you get an occurrence subtraction for this, right? And of course, still you have to evaluate the permanent, you don't know how to do this, but you can have a compact reciprocal representation in this GCT framework. Okay, you just want to conclude, thanks.
Okay, thank you very much. We'll have one question only, who's the lucky winner? Anyone? Okay. Anybody? Okay. If not, let's thank Markus again.